All right, so today we're talking about network flow. This is an extension of a problem we discussed last time. So, okay. So the high level question we're discussing last time is just a general kind of graph question. How well connected our SNT is the high level version of the question. And there's many different ways to ask this question and a lot of different applications. But we focused in on the last two on this list. So that's what's the maximum number of edge disjoint S to T paths? And what's the minimum number of edges you need to remove so that S can't get to T anymore? Okay. And so that's what we studied together. And right, so these problems are actually dual to each other in the following sense. In one problem, I'm trying to take as many S to T paths as possible, but I can only use each edge once. So I'm kind of packing it into the graph. And in the other sense, I'm just trying to take as few edges as possible, so I take at least one edge from every path. Okay, so they are in a very precise sense two sides of the same coin. And just as a immediate consequence of this incidence structure, paths go into edges, edges cover paths, you get this inequality for free. It says the maximum number of edge disjoint paths is at most the minimum number of cut edges in any ST cut. Okay, so this wasn't like, I mean, maybe we need a little bit of time to situate ourselves to know the terminology of what was going on, but otherwise the argument was kind of straightforward. So, good. And then we talked about trying to come up with algorithms for this problem. One idea is like, oh, why don't we just take as many paths as possible without, too much thinking. And well, that would work here. I found two paths in the bottom left, but it might not work. If I took this path that uses the middle edge, I'll only be able to pack in one. So greedy doesn't just work, but there was this trick, right, where we could always kind of cancel out opposite edges. So some level after taking this awkward path, I should be allowed to add the reverse of the edges I took, because I know that if I took them in the future, I can kind of unscramble it later on and recover two edge disjoint paths. So that was a main idea, a very nice idea, I think very influential over time. And that was our algorithm. So in some sense, it's kind of greedy. We are just finding one path at a time. But this residual graph kind of builds in a way for us to undo our mistakes. So by adding the reverse edge and then looking for another path and reversing it, if I took a path I really don't want in the final solution, that's okay. We still have this opportunity to kind of undo our work. So, okay. And then we proved that the algorithm was optimal. What we sort of did was, well, at the end of the algorithm, S can no longer reach T, right? So we kind of focus on the vertices that S can reach and the cut going from that side to the other, okay? Which initially had a lot of edges, but every time you added one more path, the total number of edges going from the S side to the not S side went down by one, right? Because there's a net increase of one. And in the residual graph, so now you're just counting down. Each time you add a path, this cut goes down by one. At the end, the cut is down to zero, and you've taken however many paths. So however many paths you took matches the original size of the cut. Okay? But now we had this easy, so, right, so we have this, and now we mix that with our relatively easy inequality from before, the maximum number of paths, the most, the minimum number of edges any cut. And here I have an equality, so they mutually certify each other to be optimal. Okay, so it's otherwise kind of very hard to argue that you do have an optimal solution for either problem taken alone. Right? It's really hard and rare to be able to argue that you're really correct. Right? All regular problems out in the real world don't have an answer key and grade scope and regrade requests and so on and so forth. Okay, so we actually kind of got three theorems, I guess, for free. One is just this structural aspect. The maximum number of paths is always equal to the minimum number of edges in any ST cut. And then we showed our algorithms work. That this algorithm, which is greedy plus this residual graph, will always get the maximum number of paths possible. And if you look at the residual graph, it'll reveal the minimum ST cut as well. So we also have an algorithm to compute the minimum ST cut. So we did both at the same time. It's sort of similar morally to our discussion on spanning trees. So where we left off weeks ago was, okay, what if I start adding capacities to the edges? This says how many times can you use an edge? Okay, and there's two issues. One is that you could just say, oh, capacity 3, that's like 3 copies of an edge. Why don't I just make 3 copies of an unweighted edge and use your previous algorithm? The algorithm will be correct. However, it might be very slow because the capacities can be very large and only take a logarithmic number of bits to express. And the second is, okay, what if they're not even integral? Maybe they're just real valued or something, right? Then I might start having to pack fractional paths and so forth. That'll also be painful. That said, while there are some algorithmic issues, the structural theorem we came up with is actually pretty good. So take large integral capacities, right? Okay, our algorithm might be slow, but our proof of correctness is just fine, right? So the correctness is okay. We just have to figure out how to make it fast. If you have like rational capacities, okay, let me clear out the denominators. Now I have integers. I can apply our integer case and scale back down. So that's okay. And then if I have weird irrational capacities, don't ask me why you would have irrational capacities. They are called irrational. I can approximate them by rational capacities and get sort of all the theorems plus or minus epsilon. And then I can make epsilon arbitrarily small. So that means you must have equality. Okay, so all our structural theorems still hold. All that's left is the algorithmic issue. And next time is today. Today's the future. Okay. So I think especially with an eye on non-integral capacities, it's going to be helpful to look at what's called a linear relaxation. I'll explain that in a moment. You can think of it as like a liquid version of path packing, right? So imagine like, I don't know, I can send like a molecule of infinitesimally small size from S to T along a path, and I'll use an infinitesimally small amount of the edge capacity sort of at the limit. And what we're going to do though is we're going to focus on sort of how much you're really using on each edge. So rather than trying to explicitly come up with a family of paths from S to T, what I'm going to try to do is I'm going to try to come up with an assignment where for each edge, I say sort of how much flow on it, which will correspond to how many paths in some sense use it, right? If I kind of think of every path I take as a molecule, how many molecules are running on each edge. So ultimately, this is just going to be like, you're going to assign values and you're going to be subject to some simple mathematical rules. Rule number 1 is capacity constraints. So I'm going to try to assign a value to each edge, and it cannot exceed the capacity of that edge. So here I'm thinking of every edge as a directed edge. Okay, and you can have bidirected edges going in both directions, that's fine. So each have their own capacities. And 2 is going to be something called conservation of flow. So if I'm sending flow, if I have flow going from S to T, what goes into a non-T vertex must come back out. Okay, so that's modeled by this constraint. So this looks more complicated than it really is. It's saying, okay, look at any particular vertex that's not a terminal. Okay. The left sum is summing over all the arcs going into V. And say, okay, what's the total amount of F going in? Flow is the terminology we'll use. And then the right sum is summing over all the arcs that are leaving V. And say that has to be equal. Okay, so, right, so, if I have this vertex V down here, it's saying that, okay, if you want to send like 2 units of flow on this edge and 3 units on this edge, there's now 5 units of flow going into V. There needs to be 5 coming out. So it could be like 4 and 1 or something. Okay? Those are the 2 rules. So, for example, I guess in this simple picture on the right, I can make it a little bigger. You know, maybe start sending 1 unit of flow. Say these are all unit capacity edges. And anyway, I split them here at this vertex. I'll send 0.5 this way and 0.5 this way. I'll send 1 unit of flow this way. Now it splits up 0.5, 0.5. That means there's 1 sort of in between here. Maybe I'll split them up again, 0.5, 0.5, and it rejoins to get 1. Okay, so that would be feasible. I know the vertices aren't explicitly marked out, so every time there's kind of a junction that's implicitly a vertex. But you know, 1 is going down into here, and then 2.5s are going out, so you're maintaining feasibility of flow. The amount of flow on any edge is at most 1. Okay. So there's a little bit less of, or at least the analogy has shifted. It's a little bit less discrete than before, where I'm just trying to pack paths, right? Almost everything in this class has been really, really discrete. And here you're kind of solving a math problem with some graphical interpretation, some discrete, but some continuous as well, right? So you have these constraints that are generated by a discrete underlying input, but your output is some kind of continuous thing. So it's a little bit different than what we've done before. Now, okay. So because at every intermediate vertex, what goes in is what goes out, if I want to know sort of like the total amount of flow that leaves S, okay, so S doesn't have to have parity, so there could be more going out than going in. In this case, there's 2 units of flow going out. Well, the flow can't leave the system anywhere else. What goes in, what goes out. The only place it can leave the system is at T. So you can do a summation and do this more formally, but the total amount of flow leaving S, if I had drawn flow going into S, it would be leaving minus going in. So the net flow going out of S will always match the net flow going into T. Okay, because everywhere else has to be equal. Where else is it going to go? So the max flow problem is trying to find this assignment F. It's following all the rules. It's bound by capacities. What goes in is what goes out at all the non-terminals. That's sending as much flow out from S as possible, or equivalently as much flow into T as possible. We call that the size of the flow. Okay, so again, just a little bit more mathematically defined, but maybe you can keep reinforcing this sort of analogy of trying to route as much water as possible from S to T. All right, so this is something called a linear program. Okay, let me explain why. So I guess I probably should have raised the first line, but that's okay. So first of all, our objective, right, is I want to maximize the amount of flow going out of S. So in that difference, the first sum is summing over all the arcs that leave S, the total flow, minus the total amount of flow going into S from arcs that point into S. I don't know why you would use those arcs, but still we'll have it there. You're allowed to use it. Okay. And then you over F, right? So you're just assigning at the end of the day numbers to each edge, each directed edge. Okay. And we have rules, right? So one rule is these capacity constraints. So as I assign values to the edges, the flow on an edge is at most the capacity of the edge, and it's also non-negative. You can only go in the direction of the edge. Okay, so that's one rule. And the second rule is what goes in is what goes out for all the non-terminal vertices. Again, the left is flow going in, the right is the flow going out. Okay. Now, I recognize that depending on your background, this might be like kind of painful to look at. It's a lot of summations, right? It might be look like a big system, but it's also from a certain mathematical perspective, I guess many people are now exposed to also, data science and stuff. So this is less foreign than when I taught the class 10 years ago or something, right? I haven't been teaching for 10 years, but if I had, um, these are all linear constraints. Okay, they're just sums, and equality and less than equal and greater than equal. There's no sines, there's no cosines, there's no x squared, there's no exponentials, right? It's a linear system, which while there may be a lot of constraints and stuff, right? At some level, there's implicitly, if I wrote out every equation for every edge, you'd be like, oh, this is really painful. Nobody would ever study this, right? But we sort of have this loop here. But linear systems are structurally very simple. They're the simplest things you can ask for. You can't imagine math without addition, subtraction, equal, and less than equal, right? So this is bare minimum. And right, so this is called a linear program. Okay, and it might be the only linear program we're explicitly exposed to in this class. If I had more time, maybe I would do a week on it because it's actually a very powerful tool. You can take many problems, discrete problems, and try to model it at least as a linear program. Okay, and we have algorithms that can solve linear programs in general. We don't have algorithms that can solve them once other functions come into play, right? If it's convex, okay, you can at least do a gradient descent or something, and so on and so forth. But actually getting exact can be a complicated thing. Okay, so this is an example of a linear program, and this is going to be sort of our canonical linear program in this class. So while I might not talk too much more about explicit linear programs, maybe if time permits towards the end, when you encounter them in the future, you should think, oh, max flow is the canonical linear program. Okay, so we're solving a linear program. Now, next structural question. How does max flow, which certainly feels a lot like our discussion from 2 Fridays ago, how does it relate to maximum path packings and minimum cut? Right, the input's the same. It's graph was, well, I guess capacities, but at the very least you could think of duplicating edges. So it's awfully simple. Can we formalize this connection? Okay. Well, okay, maybe I'll finally open it up because it hasn't been very interactive. Let's take max flow and max path packing. There's some quantities related to them, right? The maximum flow is 10. The maximum path packing is 20 or something. I don't know, right? Can we say anything about the two quantities in relation to each other? Even in the uncapacitated case, right, all the capacities are 1, so it's exactly like our discussion from before. Okay, why? So one of these, let's say I'm restricted to integer path pack. I mean, I can only take individual paths or something, right? So one quantity should be less than or equal to the other. One is solving a relaxation of the other would be another fancier way to say it. But which is it? They're awfully similar. They're both kind of bound by capacities. They're both trying to get from S to T. But one is always less than equal to the other. Which one is smaller? Which one is bigger? Max flow is the lesser one. So you're saying that if I can route 10 units of flow, I should be able to find at least 10 paths from S to T. Okay, maybe we can take a vote. Okay, good. So who else thinks that max flow is less than equal to max pass? Okay. Oh, we'll find out who's not voting. Who thinks that max flow is greater than or equal to max paths? Okay. Who wasn't planning to vote the entire time? And the rest of you, what happened? Okay. So we're going to show that max path is always less than or equal to max flow. So one way to do this is, well, I can take a path packing and convert it to a flow. Okay. So let's say I have a bunch of paths from S to T. Maybe it's a fractional path packing, so I can take 0.1 and 1, 0.2, but it's still subject to these capacity constraints, right? The total quantity of paths using an edge is at most capacity of that edge. Now I need to convert it to a flow of the same value. So I have a bunch of paths, so I'm kind of thinking of like, I'm writing PST to denote like all the possible paths from S to T, and X is assigning 0.1 to one, 0.2 to another, 0.3, something like this. And now I want to convert that to a flow and then check off that it's feasible and has the same size. So if I'm looking at a particular edge E, given my path packing, what should I define it as? It was the most natural. Maybe it's a little bit abstract. Imagine even just the integer case, right? You have just a bunch of paths from S to T. You want to convert it to a flow vector, which is assigning values to edges. I'm looking at a particular edge from S to T. Yeah, I'll draw a picture. Here's one path, another path. Maybe they share some edges because the capacity is more than one. And let's say I'm looking at this edge here, right? Which is shared by two paths in my terrible picture. What might I assign to be the flow? 0. So if I did that and I did that everywhere, I just end up with 0 flow. So I want to assign probably a value. Let's say there's capacities. Okay, let's say they don't share. Let's start with that. That's simpler. Yeah, that was the idea. But we can start small. Okay, they're completely disjoint. Take one of these edges. This one there. Okay. What might I assign as a flow value for that edge? Half. Okay, so if I assign 1/2 to all of the edges along all of any path, any edge I'm using, then I have two paths going from S to T, and at the end of the day, I'll get a total of 1 unit of flow leaving S, 1 unit of flow entering T. And now I can say, okay, do I satisfy the capacity constraints? Well, I'm only putting 1/2 on any edge I'm using. The capacity is 1 and I'm putting 1/2 there, so that's safe. Everywhere else I put 0, so I'm good, right? And am I conserving flow? Well, all of these flows are generated by paths, so what goes in is the same as what goes out, right? Because a path goes into a vertex, goes out of a vertex. So you're conserving flow. I mean, you're getting this conservation of flow for free at all the vertices, and your capacity constraints are actually you're doing really well because you only put 1/2 on every edge, and the capacities were 1. Of course, the total flow value is 1, and there was 2 paths from S to T, and I was hoping to show that the total flow value should be at least the total number of paths. Yeah. Yeah, so how can I get a better solution? Ah, we'll make it 1. Okay. So I'll make it 1. In general, if I had paths sharing an edge, why don't I just make a flow equal to the total number of paths using the edge? It must satisfy the capacity constraints, and you get conservation of flow for free. Okay, so this is just a very dense way to say for every edge E, let me sum over all the paths that are using the edge E, the value, the number of paths I'm taking. Okay, so any path packing can be turned into a flow by just saying, oh, for each edge, how many paths are using it. And you're going to satisfy conservation of flow at the non-terminals because the paths can't end at a non-terminal. It has to go in and out. And you're going to satisfy the capacity constraints because the paths do. You get that for free. It's going to be a mess, I think. Okay. So that will give you a feasible flow of the same size. So that shows that the max path packing is always less than equal to the max flow. And an exercise, which may or may not appear on a homework, says, oh, if you have a flow, can you extract the path packing? The answer is actually yes, and you can do it fairly quickly, but that's for later. Okay, so if I put these things together, oh, okay, sorry. So now the next question is, let's compare the minimum cut to the max flow. So I showed that max pass is less than equal to max flow. What about minimum cut versus max flow? One of these quantities is always greater than equal to the other, but which one's always bigger? Hmm? Okay, so let's look at it this way. So, all right, let's look at a particular cut. Let's say it's even a minimum cut. So let's say that I have some set of vertices around S, and I'm looking at all the edges leaving this, right? So this is like a cut of 3 or something in this picture. And now let's look at any S to T flow. So maybe the flow kind of goes like that, and that, and so on and so forth. Now, and these things can split off and rejoin each other and whatever. Okay, so now, okay. So the total amount of flow going from left to right, what you can do is you can sum up the net flow for all the vertices in A. Okay, maybe that's not a good point. So we haven't shown that yet. Yeah. So for first principles, we don't know anything, right? And what we're trying to do is we want to argue and see why it's obvious, right? So at some level, I'm really asking is why, even if you already know the facts of the matter. That's not explaining why from first principles. So, okay. So the total amount of flow leaving S is constrained by a total amount of flow leaving A. Okay, in fact, the amount of flow leaving A might be more because there might be some flow coming back, flow out, back, right? So it might actually be doubling back on itself. So that tells you that the total amount of flow leaving S is at most the size of the cut, the capacity of edges leaving this set A. Okay, so if you take the minimum of each side, so okay, the size of F, this is the net flow out of A. If you had done like going from left to right minus right to left, but that's at most amount going out, going from left to right. And this will always be at most the capacity of the cut leaving A. Okay. So this again is relatively simple. So there's two inequalities that are not too bad. I can always take a max flow and convert it into a path packing, right? And I also know that the amount of flow going from S to T is at most any cut. Okay, so max flow is less than equal to the minimum ST cut. Okay, so what happens when you put these all together, right? So we showed that max path packing is less than equal to max flow because I can take any path packing, turn it into a flow. And I showed that max flow is at most minimum cut because the flow leaving out from S is always constrained by any ST cut. Okay, so those two are, again, kind of simpler arguments, right? But now what's so powerful? Last time we showed that max path packing is equal to minimum cut. So these endpoints are equal. That means everything, right? That's going to tell us that everything is equal in between. Okay, so max flow is equal to minimum cut. Okay. Good. So max flow is sandwiched between two things we already knew were equal, and that already tells us quite a lot about the structure of the problem, right? This is nice because if you were just staring at the equations, it might not be so obvious. Okay. It's from the S side to the T side. It's a directed cut. That's right. The edges going backwards don't affect, right? I can add a ton of edges even just from T to S directly. That won't help you send flow from S to T or route paths from S to T. Okay. So now here's that question, which was really what we're supposed to ask, but we've been kind of dancing around it. How do we get a real polynomial time algorithm for this problem? Okay. Okay. So we're going to build on the same kind of residual graph idea as last time. And you can define it with respect to flows just like you would expect if you thought of each unit of flow as a fractionally tiny path. So I start with a graph like this and with some capacities. And let's say I'm sending 1 unit of flow from S to T. So that means I'm using half of the capacity of the first edge, all of the capacity of the second edge, and 1 capacity of this third edge, right? And kind of adding the reverse edge, well, just corresponding to adding some capacity in the opposite direction. Okay, so what we're going to do is once I'm sending 1 unit of flow, say from S to the top middle one, then I free up 1 unit of capacity in the backwards direction. Okay, so capacity in the forwards direction, just using capacity in the forwards direction adds an equal amount of capacity in the backwards direction. Is sort of exactly interpreting the same ideas from last time in a fractional way. Okay, so good. Now, I guess there's more diagrams here. So again, this would be an edge. I'm sending some flow, and now I have the same capacity in the backwards direction. Okay, or if there already was an existing edge in a backwards direction, let's say this was called like E prime, then I would be adding to the capacity in the backwards direction. All right. This also means that like if your algorithm somewhere in the middle is trying to send flow in both directions, you can just cancel them out. Your flow vector should only be positive in one direction or the other because you can always like, if I had flow going both ways, then I would subtract until one of them became 0. Yeah, that would be okay. Okay. Okay, so let's look at, here's our algorithm from before. And instead of trying to get maximum number of edge disjoint paths, now I'm trying to get the maximum ST flow. Okay. Now, all right, anyone want to suggest an algorithm for this? Or how to adjust our previous algorithm? So at some level, we can still try to find paths from S to T and just send flow, right? And update the residual graph. So that might look something like this. So maybe I shouldn't have erased all of that. Yeah, okay, no, that's fine. So sort of instead of our what we call taking a path and flipping edges, uh, we're going to try to route as much flow as possible. Okay, why not try to route as much flow as possible? Uh, but now sort of our notion of a residual graph is a little bit different. Uh, okay, I'm just going to update the residual graph in terms of doing the addition with the capacities. Okay. Now, this is a reasonable algorithm from before. So before I used to just take paths and take them. Now the only difference is I find a path from S to T in a residual graph, and I might as well route as much flow as possible. Okay, I don't see any reason why not. And then I'll update the residual graph, which is basically the same thing in principle as before, but it's sort of this arithmetic instead. Okay, so this is a reasonable algorithm, but it's not quite polynomial time. What would be a counterexample or a tough graph for this algorithm to deal with? Does the algorithm make sense? I know I'm describing a little bit high level. Um, oh, right now it's any path from S to T. Yeah, you can do DFS, you can do whatever you want. So if there's no restriction on the particular path, what is a graph uh, for which this will struggle? Okay, it's going to be the same sort of counterexample that we had before. Let's look at this graph here. Okay, so I have these massive edges all around the side and a relatively useless edge in the middle. Okay, and if you're not careful, then you're going to route one unit of flow, then you're going to get one capacity in the backwards direction. You route one unit of flow, one unit of flow, one unit of flow, and then okay, now that's no good, right? You're going to need 2 to the 100 plus 1 iterations to deal with this. Okay. All right. Any ideas to try to address this? Will be some heuristics or ideas? Select the intermediate vertex. Oh, okay. So if I selected this intermediate vertex, so that doesn't split the graph into two. One idea that often comes up is why don't we use the shortest path from S to T? I was never taking the shortest path in this counterexample because I was going the long ways. That would have worked. Another is, what if I try to find sort of the best bottleneck path, right? So maybe there's some smart way to say, oh, if I had taken this path, I could have routed 2 to the 100 on my first pass. That seems better than routing 1, right? That would be the bottleneck path, so to speak, the maximum bottleneck path. Sorry? Yeah, the maximum of the minimum edge along the path. Okay? Which actually, how would we compute this? Oh, there's ways to do it. Anyway, so, okay. So we're going to study the shortest path version. I'll probably just introduce the algorithm, okay, and maybe some high-level observations, and we won't be able to finish today. Okay. So this is also a very significant one because it's one of the early algorithms where, first of all, a lot of people were just fine with routing any path and be like, well, at least it works eventually, right? So Edmonds and Karp are not only going to get a strongly polynomial time algorithm, but they're going to argue in their paper that this is important. And it wasn't so obvious at the time. And anyway, so the only difference in the algorithm, which was probably already heuristic on running programs, is let's take the shortest path from S to T instead of any path. Okay, so as long as you can go from S to T in a residual graph, let's take the shortest such graph. Right, so here it is cleaned up. Just keep taking the shortest path, send as much flow as possible. So increase the amount of the flow vector along that path, update the capacities, repeat. Yeah. Number of edges. Yeah, number of hops. Okay, good. Good. Update residual graph. So, okay. So what I think I can do is I can introduce the key lemma that we need to spend a little bit more time on and discuss how the key lemma will give us a nice bound. And then next time we come back on Wednesday, we'll finish off this lemma and we'll understand everything. Okay? So the key lemma is actually a bit curious. Okay? It says that for every vertex v, right? If I kind of look at the distance from v in the residual graph in terms of like BFS layers, it says that over the course of the algorithm, this distance never goes down. V only gradually moves further and further away from S for every vertex V. So something about repeatedly using the shortest S to T path will guarantee that the distance from S will never decrease, right? This should be surprising because we're trying to route flow and suddenly distances have entered a discussion, right? It actually comes from a certain interpretation of the dual LP, but that's slightly besides the point. Okay, so let's see why this is useful though. It's also not clear why this is even useful. It seems like just a curious observation. Okay, so now let's assume this key lemma is true and look at a particular edge E that's going from U to V. And let's study the distances from S to U and distance from S to V in the residual graph. Okay. So suppose I find a path and that results in removing the edge E. So removing means I've used up all the capacity. I remove the edge from the residual graph. Okay. Well, that means that whatever path I took must have used that edge, which means that U came right before V, just like in this picture. Okay. My watch is slow by a minute. So E was in the shortest S to T path. And if it's on the shortest S to T path, then U had to be one hop before on the shortest path. So you have something like this. And if this is sort of the breadth first search level of U, level of V, we know that level of V is equal to level of U plus 1. Okay. I think I'll need about 2 minutes. Now, what happens when u to v is added back into the residual graph? Right? So edges can appear and disappear from residual graph as they get back capacity. So if it gets added back, that means that the opposite direction was in the shortest S to T path iteration before, and we augmented along that path. Right? It's the only way to add capacity back and get u to v back in the graph. And that means that you had something like this. V was one hop before u, so level u was equal to level v plus 1. Okay, so a little confusing. So we have these two things, right? Every time E is removed, level of U is one less than level of V. Every time E is added back in, that means level of V was one less than level of U. Okay? Thus, if you combine these two events, if the edge leaves and it reappears, right? What do I know? I know the two levels have actually switched order. Switched order twice. Flipped and flipped. Okay? And I know the levels are always non-decreasing. So if I have one before the other and they flip, what does that say about the levels? So if they can't go down but they flip order, the first one must have gone up. Okay? So every flip, right? The maximum level is n minus 1, that's the maximum distance, or it could become infinity. So every edge gets deleted at most n times from the graph. Okay. Last observation. Rats. Okay. I claim that every iteration I find the shortest S to T path and route as much flow as possible is going to delete at least one edge from the residual graph. The question is why, and then you're free. I pick an S to T path and I route as much flow as possible. I claim it's going to delete at least one edge from the residual graph. Yeah, so it must be using up the whole capacity of, whatever is the smallest capacity edge on the path. So we route as much as possible. So every edge can only get deleted n times. Every iteration deletes one edge. That means there's mn iterations. Somehow studying the distances, and now you have a strongly polynomial bound on number of iterations. That's not at all obvious. You put all that together, mn iterations, m time per iteration, you just do BFS. Mn iterations, you get m squared n time. Right? This is like highly non-trivial, and I probably rushed it a little bit and killed some of the drama and suspense. But what it's really saying is, somehow this lemma is really important, right? Trying to show that the distances never go down, that then will lead to this strongly polynomial running time. So that's what we'll do next time. Just focus on why the distances don't go down if I focus on shortest paths, and then that'll complete the proof of this algorithm. All right, thanks. Sorry for going over. All right, so network flow. We started this on Wednesday, so I'll just catch up through what we covered, and not everyone was here, but hopefully this preview will help. So we're looking at these kind of connectivity type problems. High level question is how well connected is S to T, which you can ask in many different ways, but we focused in on two questions. How many paths can you pack from S to T? And on the dual side, how many edges do you need to remove to separate S from T? And one inequality is immediate from this dual relationship. And then we start developing algorithms. The simple greedy algorithm doesn't work because if you take the wrong path on this simple example, you end up with one path instead of two. But the idea we introduced was, if you think about it, after I sort of take an edge in a forwards direction, I can sort of take the opposite edge later, knowing that I can uncross any paths that use both. So that was the main innovation. We introduced these opposite edges, and that lets us sort of undo mistakes made by a basic greedy approach, right? And that turns out to be all the difference. And we're able to prove that the algorithm works by sort of looking at the residual graph at the end and things like this. Now, the key, I think a really important feature of the proof in the analysis is that we already knew that the maximum number of paths is at most a minimum ST cut. And in the proof, we studied an ST cut suggested by the residual graph at the end. And we're only able to prove our algorithm worked because we had a matching cut of the same size. Okay, so two things happened. One, we also got an algorithm for computing the minimum cut, but at some level, these sort of dual problems, it's hard to solve one without the other. It's hard to justify that your solution is optimal, without comparing it to the other. So this occurs in some other, other problems in computer science. Even something like convex optimization, the gradient is a dual certificate. But but this is maybe this in spanning trees will be in our class our canonical example of sort of two sides of the same coin really being very important. So before spring break, we had started to worry about, okay, what if instead of edge disjoint paths I have capacities? Okay, so for example, your algorithm could be very slow and things like this. Right. But I wanted to quickly point out that although we have some algorithmic issues, our sort of duality theorem is still okay. You can interpret it for capacities and it's still equal, so things are still very nice mathematically. And it was just an algorithmic question that we were left with. So, okay. I feel like I'm going to spend the whole time recapping last class. But so we introduced a slightly different version of the path packing problem, okay? Where instead of trying to route sort of explicit discrete paths, I sort of imagine trying to send as much water from S to T, where the capacities of the edges are sort of like how much water can go through per unit of time or something like this. So as I send water from S to T, so water goes into S, it leaves T, that means like at an intermediate vertex that's not S or T, what goes in has to be what goes out. Right? So in this kind of example, you have 1 unit of flow, and it splits off into 2 units of 0.5 flow. And that's okay. What came in is what came out. The other rule, again, is that the amount of flow you send on any edge is at most the capacity. So this is some example where we assume every edge has unit capacity. So you'll see all the values are at most 1. Right. And so this is another problem. If you think about it, since for all the middle vertices, what goes in is what goes out, the total amount of water leaving S is exactly the total amount of water going into T. There's nowhere else it can go. And you can do this more carefully mathematically by checking out the sums and stuff. But if you just buy into the analogy, then I can sort of refer to, the size of the flow to be like the amount of flow leaving S or the amount of flow entering T. And there's this clear notion of size. Now, I briefly mentioned that this problem is also a relatively simple mathematical problem in the following sense. It's not a simple problem in the sense that you can have many variables and many equations, but it's simple in the sense that every equation is like a bunch of sums. The sum here is equal to the sum here. This value is less than equal to that value. So everything's a linear function plus some inequalities. Okay? So that means we don't have things like x squared, e to the x, sines, cosines, and other painful things. And while this may be the only example of a linear program we'll see in this class, depending on time at the end, it's good to know that there are a broad class of computer science or optimization problems where the first step is to try to write it out as a linear program and see how far that gets you. Okay. Max flow min cut is a very nice, well-behaved linear program. So if you run into a linear program in your promising future, you can think of max flow min cut as just an example. Like, okay, I've seen a linear program before, and it'll get you started. Okay. How does this relate to path packing? I'll go quickly. they seem similar. I'm trying to send stuff or, connect S to T. And you can make this a little more formal. If you have a bunch of paths going from S to T, I can define a flow, which I didn't say this explicitly just now. It's really just assigning values to edges, which is how much water is going down the edge. By saying, okay, let me look at this edge. How many paths use that edge? And that'll give me some assignment of values to edges. Okay? And what's nice is, first, for capacity constraints, the number of paths you're taking is the most to capacity edge, so your flow will also have this property. And then maybe the cuter one is conservation of flow. A path going from S to T, every time it goes into an intermediate vertex, it comes out of that intermediate vertex. So the amount of flow it's kind of contributing to both sides is always the same. So you automatically get conservation of flow. The result then is that every time you have a feasible path packing, you can convert it to a feasible flow, ST flow, of the same size. So the max path packing always less than equal to the max flow. And the other side is, how does max flow compare to the minimum ST cut? If I look at any cut, like I have these vertices around S that I call A, the amount of water that's leaving S is going to be bounded by the total capacity of edges leaving A. Okay? So you're going to get that the size of S is always at most the capacity of any ST cut. Okay, so those two just follow. Not too difficult, just kind of carefully working through some definitions. But if you put that all together, you'll find that max flow is now sandwiched between the path packings and the min cuts that we did a few weeks ago. And so you have equality all the way through. So max flow is actually a linear relaxation of the path packing problem. Okay, but it's still bounded by the minimum cut. Okay, so with that, we shift focus to this max flow problem. And we try to get some strongly polynomial running times. Okay. So we can sort of work by analogy from our Fulkerson path packing algorithm, where I can have a residual graph where kind of instead of thinking about reversing edges if I'm routing one unit of flow, I can add one unit of capacity in the opposite direction. Okay, so because I've routed one unit of flow going up, now there's another unit of flow going down, and this capacity has gone down by one because I've used up one. Okay, so what that means in the physical analogy is if I'm pushing water in the opposite direction, the two directions would kind of cancel out. Okay, so you're really just pushing back water as opposed to literally sending water. So that's the main idea. And otherwise we can take our previous algorithm and say, okay, why don't I just keep trying to find paths in my residual graph and route as much flow as possible? Repeat, repeat, repeat. That sounds good. That's totally like analogous to what we did a couple weeks ago. The only problem is if I give you a graph like this, it's a little bit harder to see now because I drew on it with a crayon last class. But there's a huge capacity edges here, huge capacity edges here. But if I'm not careful, I'll keep routing one at a time, and I won't terminate very fast. Okay. So the innovation we introduced last class by Edmonds and Karp, although it might have been already heuristic, is let's try to take the shortest path every time. Okay. So the only difference from before is we're always going to find the shortest path from S to T. That's measured in number of edges. And we'll route as much flow as possible and update the residual graph. Okay. So, right. We're almost caught up. So that's the algorithm in a cleaner form. I'm just going to keep routing as much flow along the shortest path. And then we started the analysis. So what we did last time was we introduced this key lemma and explained why it's helpful. And today we're supposed to work out the key lemma. So we're almost there. Okay? So the key lemma is that as you keep routing along the shortest path, right? So in the residual graph, you have some vertex v, right? And I can count its distance from S in the residual graph. How many hops away it is from the source. And the key lemma, and this is gonna, we'll have to be careful to show this, is that the vertices, any individual vertex is only moving further away. It never gets closer to S. Okay, so this is sort of bizarre, right? Because we're working on a flow problem and suddenly we find ourselves quite interested in the shortest distance. Okay, so this is quite odd. But anyhow, the claim is that the distances are always increasing. So to try to demystify a little bit, we work through why it's useful, okay, or why it leads to a useful running time. So all I know right now is that, I'm just promised that the vertex distance always increases from S in the residual graph as edges get added and removed from the residual graph. I should clarify that when an edge's capacity becomes 0, then we just remove it from the graph. I can't route any flow. So, okay, let's look at a particular edge from U to V. Okay? And sometimes that edge will be in the residual graph and it'll be removed from the residual graph because we used up all the capacity. And sometimes later, it could be that we route flow in the opposite direction and then E suddenly has some capacity, it reappears in the residual graph. Okay, so this edge will come and go over the course of the algorithm. And so whenever the edge is removed, that means it was just on the shortest path from S to T, right? Because we're always sending flow along a shortest path. So that means in terms of the layers, or I guess I wrote them as levels, U was one level before V. Okay, because you always have to go up a layer if you're doing breadth first search. Okay. On the other hand, whenever the edge is added back into the graph, that means I sent some flow in the opposite direction right before, which means that the opposite edge was on the shortest S to T path. Okay, which means that the level of V was one less than the level of U. So each time an edge disappears and comes back, it comes back flipped. Or, no. Yeah, it kind of comes back flipped. Okay? And, okay, so why is this useful? So, okay, yeah, so here are these two observations, right? So I have these I have this edge from U to V, and it disappeared and it came back. But I know in that time, the relative order of the endpoints had changed. That's all we know. Okay? Now, I want to argue that one of these endpoints must have actually gone up. So how do we argue this? Yeah, so it can't go down. So the only way for this to be bigger is, that first endpoint really had to have gone up at least 2, even if the other one didn't move. Okay. So I can charge that edge, disappearing and coming back to that vertex making some progress away from S. Because this particular vertex, what's the maximum distance it can be from S? Yeah, n minus 1 and then followed by infinity, right? So U can only go up so many times. So now I'm saying, oh, every time the edge disappears, one of the endpoints went up, and each endpoint only goes up so many times. Okay. So if we put all that together, right, then I conclude that this particular edge is only going to get added, deleted and added from the residual graph n minus 1 times. Okay? Because whenever an edge gets deleted, I can charge that to one of those endpoints making progress, and it can only make so much progress. Okay, good. So now, what is the final touch? How can I argue now that the whole algorithm finishes in polynomial time, polynomial number of iterations? So I've promised to you that each edge gets deleted from the residual graph at most n times. Yeah. Because yeah, and each algorithm will remove one edge because we route as much flow as possible. So if I route as much flow as possible, it's going to use up all the capacity of some edge along that path. That edge will be removed from the residual graph, and so it'll be one of these n times for that edge. Okay. So you put everything together, and you need mn iterations. Each iteration, you're just finding a path. That's om time, and you get m squared n. Okay. But it's a quite subtle analysis because it's focusing on these distances from S, which was not at all obvious that this flow problem was going to have anything to do with distances. Okay, so that key lemma is really important. So, okay, let's try to prove this lemma. Okay, so that lemma says that the distance from S to V in the residual graph will never decrease. If we do that, then we're done. Okay, so somewhere in here, we're going to have to use the fact that we're always augmenting along the shortest path. We haven't actually used that yet. Okay, so any ideas about how to do this? High-level ideas of an approach? Okay, so we are going to try to prove this by induction on the level of V after updating the residual graph. Okay, so, okay, let's see what's here. All right, so in the base case, the smallest level is 0, right? Now, which vertices can even have distance 0? Just S. Everyone else is at least one hop away. So there's nothing to do here. It's just S. That never changes. So base case is okay. Okay. All right. So now in the general case. Okay. In the general case, let's let V be a vertex that's at like level beta after updating. And I'm letting alpha denote the level before updating. Okay. And I guess I'm letting U be, so there's some, that means there's some path in the after graph from S to V with beta edges, and that's the shortest one. Okay, that means there's some vertex before, and we'll call that U. Okay, so whatever is the shortest path, it'll go through U to V. Okay. Now, so that means U has level beta minus 1, right? So, so that means what's the U's level over here? Well, okay, so by induction on beta, I know that its level over here is at most beta minus 1 before. Okay. So I'm trying to argue levels never go up. I'm worried about V. but the claim must already hold for u by induction on that level afterwards. Beta minus 1 is less than beta. So wherever u is, I actually don't know where it is in relation to alpha, but it's at some level less than or equal to beta minus 1. Okay? Now, okay, good. No, it should be at most beta minus 1 before augmenting. Okay. You want to argue that's exactly beta minus 1 before? Well, maybe you could have been like very close, and it could have been on the shortest path, and then deleting this edge could have been very important for you. There's nothing about the edge. UV might have been in the graph before, it might not have. No, this is before augmenting in a particular iteration and updating the residual graph. Yeah, we don't know. We don't know. So we're not assuming anything. We just know there was an augmentation and we have to work through the possible situations. Yeah. So, okay, so good. What else do we have? Um, okay, so, okay. So if uh, alpha is bigger than uh, why did I say this? All right, let's see how this plays out. One sec. Wonder if I made a mistake. Okay, okay. Good, good. I confused myself. So if okay, so if by contradiction alpha was at least beta plus 1, right? So that's what we're claiming can't happen. Okay? Then we know that okay. All right, so I know that okay, that means that that u has to be somewhere over here to the left. Okay? And the augmenting path is taking some kind of shortest path, so it can't go backwards. Okay? So v to u was not on the augmenting path because that would be a backwards edge. Okay? And that means u to v, since u to v appears in the graph afterwards, okay, and we didn't use v to u last time, so u to v had to be in the graph before as well. Okay? But then that implies that that would imply, there must be one edge, and that, so okay, we must have something like this. U is some level here, right before. It's one hop away, and this is at most beta minus 1, which would force alpha to be at most beta, and then we'd have this contradiction. Okay, I didn't do it as slick as I had rehearsed it in my head. Right. Yeah. So that is it. Okay, so we get this contradiction. I didn't do it perfectly, but are people okay with this? I can do it again. No. Sorry. It has to be less than beta minus 1 before augmenting. Because we're doing induction on beta. So level U is less. So by induction, this is true. Yeah. And then you kind of work it through. It's like, oh, you must have gone backwards and forwards, and then you have some issue. Okay. Okay. So it's a little delicate, but that's the whole thing. So with this, somehow taking the shortest path, yeah, you can go back. Yes. So if alpha was at least beta plus 1, which we're saying is by contradiction. So in print, we want to show that alpha is less than beta or less than equal to beta. Okay. But if alpha was bigger than beta plus 1, okay, then U would be earlier than V, even before. Because I know V is at some alpha, which is at least beta plus 1, and U is at most beta minus 1. So in the before graph, if alpha was actually bigger than beta, if V was actually further before, um, I know that U is to the left of V before, is closer to S. Okay. Now, all I know about the augmenting path that was in between them is it took some shortest path. So it would never go backwards. It wouldn't like go to V and then back to U and then forwards, right? The shortest path would always advance through the layers. So consequently, V to U was not on the shortest path. So I did not send flow from V to U previously, but I do have some capacity from U to V afterwards. And that capacity, U to V was an edge after, and that edge did not get introduced by the previous augmenting path because it didn't use the opposite edge. That means U to V must have been an edge before. But then that would require V to be at most one level away from U. And then that would require the level to be at most, that should be beta, not beta minus 1. At most beta before augmenting. And now I have this contradiction. I said, oh, suppose by contradiction alpha is at least beta plus 1. But then that would still require it to be at most beta. That can't be possible. So this must have been wrong. Yeah. Okay. Yeah. Yeah, so we assume by contradiction that alpha is greater than or equal to beta plus 1. If we assume this thing was true, that would lead to a contradiction. So this cannot be true. That gives us alpha is less than or equal to beta. Yeah, this is by induction. Yeah. So, other questions? Yeah, I guess it's probably one of the more subtle arguments we've had so far. Um, okay, so somehow in this manner, by always taking the shortest path from S to T, we get that strongly polynomial time algorithm we wanted. This works even with irrational capacities, with very large capacities, whatever, right? Although the analysis is very indirect, it's focusing on these distances from S in a residual graph. There is some interpretation based on the dual LP, but Yeah, so there's a sort of dual argument focusing on distances, and that's how you ultimately argue this algorithm runs in polynomial time. Um, yeah, I mean, there's some historical significance to this because this is one of the early problems for which it wasn't obvious how to get a polynomial time algorithm, and it was a very, subtle argument to get a polynomial time algorithm. So it wasn't obvious for 20, 30 years. Um, and the paper will also advances an argument in favor for polynomial running times, which was not that obvious. It wasn't the first paper to make such an argument, but it's one of the early ones. And just even making this distinction that others were not making. Other questions?